So we talked about various aspects of data communication and networking, and we saw the digital transmission, analog transmission, the multiplexing, the switching, etc. But underlying transmission, there is always a possibility of errors. In every wake of life, we'll find errors, and this transmission is not away from it. Today, we are going to see the error detection and correction. What can be the errors? What are the type of errors? And what are the correction techniques which we can employ? So data can be corrupted during transmission from one point to another. It is not necessary that 101 has been sent and you receive 101 always. You may receive 010 maybe. So some applications require that the errors be detected and corrected. Some application may not stand any sort of errors. So let us first discuss some issues which are related directly or indirectly to your error detection and correction. We'll see the types of errors, redundancy, detection versus correction, forward error correction versus the retransmission, the coding, and the modular arithmetic. In a single bit error, only one bit in the data unit has changed. See, this is 010, and if it is received as 000, there is only change in the second bit, which is one bit. This is called as single bit error. Only one bit is changed. This is a single bit error. All others remain the same when they are received, but one bit has changed. So 0 has changed to 1. But a burst error means that two or more. One is single bit, but beyond that we call them as burst error. It means two or more bits of the data units have been changed. This is the burst error, say of length 8. This is length of the burst. The error is 8 bit. How? From this point to this point, 0 has changed to 1. So this is an 8 bit or 8 bit error. This is the length of the burst error. And we call it as a burst error of length 8. These are the corrupted bits. To detect or correct errors, what we are going to do? We may need to send certain extra bits with data. So if this is the data, we will add few more bits. These are added bits. We add certain bits and we also call them as extra or redundant bits to detect or correct the errors. This is the structure of encoder and decoder. And when the sender sends, this message is generated. Then the message and the redundancy, that is the extra bit, is being sent through an unreliable transmission. The received information is checked. There is a checker is there. Either we discard the message and we request, either we may request or just ignore, or we can ask or request the sender to retransmit the data again. Or we may take up one more issue or one more way to correct the data which we have received, and then the message can be transmitted or received or given, submitted to the receiver. So we concentrate on the block codes. We leave convolution codecs to certain advanced texts. We'll see the block codes. In modulo and arithmetic, we use only the integers in the range of 0 to n minus 1. 0 and n minus 1, they are inclusive. This is modulo and arithmetic. We'll be able to understand it more. What it means: XORing of two single bits or two words. What is XORing? XORing means if two bits are same, say if they are either 0 or they are 1, if we XOR them, XOR sign is given by this symbol. So if we XOR two bits which are same, we'll always get the error as 0. But if the bits for XORing are different, say 0, 1 or 1, 0, we'll always get 1. So how can we XOR two patterns? See, because they are similar, it will be 0. All similar will have 0. All similar will have 0. But the different one will have 1. Different one will have 1. This is the XORing. In block coding, we divide our message into blocks, each of k bits. And we call these k bits, that means you have a message, you divide them into blocks and each has k bits. So these k bits are called as data words. We add r redundant bits to each block. Means if this is a block, we add r here, we add r here, we add r to this block. So we add r redundant bits to each block to make the length as what will be n. This will be k plus r, k bits, and r redundant bits. So the length will be k plus r. So the resulting n bit block will now be known as code words. Previously only k was known as data words. Now k with r, that is the redundant bit, will be known as code words. We'll see all these: error detection, error correction, Hamming distance, minimum Hamming distance. So we have just talked about the data words and code words. What are these in block coding? These are k bits, different blocks. So you have 2 to the power k data words, each of k bits. How many are these? 2 to the power k. So these are 2 to the power k data words, each of k bits, as you can see. But in case of code words, when you have added the redundant bit, it will be n bits, and then as we have just seen, they will be equal to k plus r. K is this, and r added. Each of n bits, so only 2 to the power k of them are valid. Let us take an example. If 4b or 5b block coding we discussed in the previous chapters is a good example of this type of coding. In this coding scheme, k equal to 4 and n equal to 5. As you saw, 2 to the power k equal to 16. This is 16 data words. That is 2 to the power 4 will be 2 to the power 4 will be what? 16. So 16 data words. And if we have n equal to 5, what number of code words will be there? 2 to the power 5, that will be 32 code words. So we saw that 16 out of 32 code words, 16 out of 32 code words are used for message transfer, and the rest are either used for other purposes or they are unused. This is the process of error detection in block coding. A sender sets, this is the data word with k bits, then a generator will be there for making it code word because k will be added with r redundant bits, so this will be n bits. This is the unreliable transmission. Now you have a code word with n bits, and the checker will either extract or discard the code word which is coming. And the data word will remain as k bits because we are only interested in k. Whatever you add r is at your disposal, or it's your concern, not my concern. My concern is only if I send k bit, I have to receive the k bits properly. You add r, you try to check it, it's very good. That is what we are looking for. So let us assume that k equal to 2 and n equal to 3. So we'll see the table. This table, a code of error detection. We have 00 data words. For that we have 000 code words. For 01 we have 001 added. For 10 we added 1, 1 we added 0. So with respect to this table, it shows the list of data words and code words. We'll also see how to derive a code word from the data word. So assume the sender encodes the data word 01 to 011. We added 1 and sends it to the receiver. Just consider certain cases. The receiver receives 011. It is a valid code word. So the receiver will extract the data word 01 from it. No problem. The code word is corrupted during transmission. So 011 was the code word. 1 was added. So the received was 111. This is not a valid code word. We require 011. It is discarded. Now the code word is corrupted during transmission. 011 needs to be there, but we got it as 000. This is what we got, because the code word is corrupted during transmission and 00 is received, and this is a valid code word. Say the receiver incorrectly extracts the data word 00. Then as we see that here this 000 is a code word and this is correct. So what we are suggesting is, forget about this previous case, but 000 is valid. This is a valid code word, but the receiver incorrectly extracts the data word 00. And what we have sent 01, 2 corrupted bits have made the error undetectable. So 011 needs to be sent because of 01. but the data which came, or the code word which came, was 000. So there is a change in 2 bits. That is, one has changed to 0, one has changed to 0. So actually 000 was received, but the receiver extracted. It assumes 00 to be the correct one. So error detecting code can detect only the types of error for which it is designed. Other types of errors may remain undetected, as we have just seen. So the structure of encoder and decoder in error connection, what it will be? We have seen that k data word will be there, k bits data word, n bit code word, and now this is for error correction. So we will not ask the sender to send it again. No, we'll try to correct it. This is error correction. So let us add more redundant bits, as we have seen in the previous example, to see if the receiver can correct an error without knowing what was actually sent. So now we add 3 redundant bits to the 2-bit data word, and let us make it 5-bit code word. We'll see a table which shows the data words and code words. Let us see it first. So these are the 2 data word, or this is the data word. We have added 3-bit more, that is made this 2-bit data word to 5-bit data word, and this 5-bit we have added, and this data word can be corrected using these 3 redundant bits. Let us see. So we have seen the table of data words and code words. Assume that the data word is 01. The sender creates the code word like 01, 011. The code word is corrupted during transmission, and what received is 01001. Okay, so this bit has changed. Okay, so first the receiver finds that the receiver code word is not in the table. First of all, this is not there. This means certainly an error has occurred. So the receiver assumes that there is only 1 bit corrupted. So it uses the strategy to catch the correct data word. How? Comparing the received code word with the first code word in the table. That means this received with the code word in the table. The receiver decides that the first code word is not the one that was sent, because there are 2 different bits. This one and this one is 0 and 0. So with the same reason, the original code word cannot be the 3rd and 4th in the table, as we have seen here. It cannot be 3rd, or it cannot be this one. So the original code word must be the second one. That means this one. So the original code word, second one in the table, because there is only one that differs from the received code word by 1 bit. So the receiver replaces 01001 with 01011 and consults the table to find the data word, which is, what is for 01011 or 01011? It is 01, and this is what we have actually said. This is how we use different techniques, adding code words, redundancy, to find the actual correct code. The Hamming distance between 2 words is the number of differences between corresponding bits. The Hamming distance between 2 words is the number of differences between corresponding bits. So let us find the Hamming distance between 2 pairs of words. The Hamming distance of 000 and 011 is 2. Why? Because when we XOR these 2, there are 2 ones. How many ones are there? 2. So the Hamming distance is 2. If we XOR these 2, we get number of ones as 3. 1, 2, 3. So the Hamming distance is 3. Minimum Hamming distance is the smallest Hamming distance between all possible pairs of which are in a set of words. Again, the minimum Hamming distance is the smallest Hamming distance between all possible pairs in a set of words. So let us find the minimum Hamming distance of the coding scheme we saw in table 10.1. We first find the all Hamming distances, that is 00011. Hamming distance is 2. We have to take the XOR and find the number of ones. So in all, we have the Hamming distance as 2. 2, 2. So the D minimum, or the minimum Hamming distance, is 2. Let us make it or take it for 10.2, and I hope you remember or recall the 10.2 table. So let us first find all the Hamming distances. We have to XOR these 2 and find out the number of ones. This will be 3, 3, 3, 4, 4, 3. So the minimum is 3. Minimum having distance for the coding scheme table 10.2 is 3. So to guarantee the detection of up to S errors in all cases, the minimum having distance in a block code must be D minimum, which is equal to S plus 1. Okay. We'll see with an example, don't worry about that, because to guarantee the detection of up to S errors in all cases, the minimum having distance in a block code must be D minimum, which is given by S plus 1. The minimum having distance for our first code scheme is 2. This code guarantees detection of only a single error. For example, if a third code word that is 101 is sent and one error occurs, the received code word does not match any valid code word, as we have seen. So if 2 errors occurs, however, the received code word may match a valid code word and the errors are not detected. But the second block code scheme has a minimum distance or minimum having distance of 3. So this code can detect up to 2 errors. How? We see that when only any of the valid code words is sent, 2 errors create a code word that is not in the table of valid code words. The receiver cannot be fooled. However, some combination of 3 errors change a valid code word to another valid code word also. So the receiver accepts the received code words and the errors are again undetected. This is the geometry concept for finding D min in error detection. We have just seen how we can do it by XORing and finding the number of ones and finding all the distance and taking the minimum. So for this geometry concept, let us see. This is any valid code word, and these points are any corrupted code word with 0 or S errors. So this is the D minimum, that is the minimum having distance which is greater than S. What we saw, the radius is S, but the minimum distance is greater than S. This is what we saw and learned in the previous sections. So how we can take this geometry concept for finding D minimum or having distance, minimum having distance in error correction. So in this case, this is the territory of X, this is the territory of Y. Okay, territory of X, territory of Y. Here, all these bits are there, and you have radius T. This is radius T, so D minimum is greater than 2T. So this is the concept of finding D minimum in error correction. This is any valid code word, and these points are any corrupted code words with 1 or T errors. So to guarantee correction of up to T errors in all cases, the minimum having distance in a block code must be, D minimum should be 2T plus 1. Okay. So a code scheme has let's take one example now. A code scheme has a having distance D minimum equal to 4. What is the error detection and correction capability of the scheme? So this code guarantees the detection of up to 3 errors S equal to 3. How? But it can correct up to only 1 error. In other words, if this code is used for error correction, part of its capability is wasted. So error correction codes need to have an odd minimum distance, 3, 5 or 7. I hope you got the idea. So now we see the linear block codes, because almost all block codes used today belong to a subset of linear block codes only. A linear block code is a code in which the XOR, exclusive OR, that is addition modulo 2, of 2 valid code words create another valid code word. So you'll see the minimum distance for linear block codes and some linear block codes also. In a linear block code, the XOR of any 2 valid code words create another valid code word. So we'll see that the 2 codes we defined in 10.1 and 10.2 table belong to the class of linear block codes or not. The scheme in the table 10.1 is a linear block code because the result of XORing any code word with any other code word is in result a valid code word. For example, you can XOR any of these and you can create the 4th one. Second and third, and you can create the 4th one. And in the table 10.2, if you recall, it is also a linear block code because we can create all the 4 code words just by XORing 2 other code words. So in our first code, that is in table 10.1, the number of ones in the non-zero code words are how many? 2, 2, 2. So the minimum having distance will be, the minimum is 2. But in this, our second table 10.2, I hope you recall these two tables. Otherwise, you just go back and see, watch it once more. So the number of ones in the non-zero code words are 3, 3, 4. So the minimum will be 3. A simple parity check code is a single bit error detection code in which n is equal to k plus 1. You know what n and k are? K bits and code word. These are the data words. These are the k words. Where d minimum is equal to 2. That is the minimum handling distance equal to 2. This is a simple parity check code. C54 means you have 4 data words. The code words are what? 5 bits. So this is the formation of simple parity check code. And this is how the encoder and decoder for simple parity check code works. The sender sends the data word A0, A1, A2, A3. The generator adds a parity bit to this A0, A1, A2, A3 as R0. This is an unreliable transmission. Now, this was R0, received, or R0. So, Q0 was received here. And the code word was B3, B2, B1, B0. It is checked with some syndrome. And then with decision logic, we can either accept or we can discard. So, let us have some transmission scenarios. Assume that a sender sends the data word 1011. And the code word created from this data word is what? 1011. 1011, where is 1011? Can you find it? 1011. So it will be this one, 1011. So 10111 will be there. So for 1011, we have data word as 1011 from the table we have seen, which is sent to the receiver. So we examine the 5 cases. There may be 5 cases. First is no error occurred. That the received code word is 10111. The syndrome is 0. The data word 1011 will be created. No problem. Say one single bit error changes A1. What we mean is the received code word is 10011. We received 10011. So there is a syndrome which is 1. That is 1 bit. This bit was changed. So the syndrome is 1. So no data word is created. One single bit error changes R0. So the received code word is what? 10110. Say. The received code word is, the send was 10111. The received was 10110. This one. Again the syndrome is 1. No data word will be created. Now an error changes R0 and a second error changes A3. Now we have the code word which is received as 00110. Again, the syndrome is 0 because the data word 0011 is created at the receiver. This is a valid code word. We have to note that the data word is wrongly created due to the syndrome value. 3 bits, say A3, A2, A1, they are changed by error. Now the received is 01011. Received is 01011, and the send was 10111. 10111. So this has changed. This has changed. 3, A3, A2, A1 has changed. The received code word is this. The syndrome is 1. The data word is not created. This shows that the simple parity check guarantees the detection of one single error. It can also find any odd number of errors. We have seen in the 5 cases. So simple parity check code can detect odd number of errors. A Hamming code discussed, we have d minimum equal to 3. So the relationship between m and n in this code is n equal to 2m minus 1. So this is 2-dimensional parity check code. We have column parities, we have row parities. This is how we design row and column parities. One error affect 2 parities, means this one and this one. 2 parities. 2 errors affect 2 parities, these two. This is the 2-dimensional parity check code. And 2-dimensional parity check code, if there are 3 errors, that means this one, this one, this one. So it affects 4 parities, 1, 2, 3, 4. Now 4 errors cannot be detected, right? This is a Hamming code 7, 4, that is you have data words as 4 and 7 as the code word. So 3 extra bit has been added to the data words. And the structure of the encoder and decoder for this Hamming code, they are 4 sent, 3 added, 4 received, 3 received, so we have a checker. Syndrome is S2, S1 and S0. This is a correction logic and the data word will be retrieved. So the logic decision made by the corrections logic analyzer will be like this. If the syndrome is 000, error is done. If syndrome is 001, the error is at Q0 and likewise. This table is there. So this actually shows, what I want to tell you, that this syndrome has actually told you that depending on the syndrome, we can easily find out where the error is. Now let us trace the path of 3 data words from the sender to the destination. The data word 0100 becomes the code word as we have seen in the table. The code word say this is received. The syndrome is 000. So the final data word is what it will be. Say 010011. Okay. So in this case, because the code word is 010011 and we have received 010011, that is 1 as change. The syndrome is 0. So the data word say 0111 becomes this one from the table. The syndrome is 011. After flipping B2, that is changing the 1 to 0, the final data word will be easily 0111. And the data word 110 becomes the code word 110100. The syndrome is 101 and we flip the B0. What I'm trying to say is we just have to see this table. We're just flipping according to what we have received. What we receive in the S1, this S2, S1, S0. Right? So the data word 1101 becomes the code word 110100. Syndrome is 101. We flip the B0, we get 0000, the wrong bad data word. This shows that our code cannot correct 2 errors. So we need a data word of at least 7 bits. As we have seen, let us calculate the values of k and n that satisfy this requirement, that we need a data word of at least 7 bits. So we need to make k equal to n minus 1, that is which is greater than or equal to 7. That is 2m minus 1 minus 1. M should be greater than or equal to 7. If we set this is the formula which I already told you with respect to n and m. And in this case, we set m to 3. The result is n equal to 20, 3 minus 1, k equal to 7 minus 3 or 4, which is not acceptable. But if you set m equal to 4, n equal to 15, k equal to 15 minus 4, that is 11, this is going to satisfy the condition. So it will be 15, 11. And you have to go back and see what condition I told you, because that is very important. So burst error correction using Hamming code, how it can be corrected. These are various code words. This is a data unit in transit, whole data. Here is you have burst error. So now the receiver can receive it and you can correct the burst error. So this is the first part. We'll be taking one more section of this. Till then, thank you so much. Take care.